Okay, hello everyone. I hope you are all well, and please stay in home unless it is absolutely necessary. I know that these are hard times, but this too will pass. Try not to focus on the distraction of the disaster, but let's focus on how we can rebuild everything when this pandemic is over. Use this time really well. You can improve your knowledge, you can improve your knowledge and improve your skills. Keep your spirits up. You cannot calm the storm, but you can calm yourself. So please focus on how we can use this time efficiently and in a good way. So this is our first video, so I'm trying this for the first time and see how it works. So I canceled the lectures even before the university canceled them due to the pandemic, and now we are starting this online lectures. Today, since this is our first video, instead of talking something new, I wanted to recall what we were doing for the first homework and try to recap what we have done so far. So, let's recall what we were doing. We were working on present. Here is the picture of present. I think you are now a lot more familiar than anything else. So, I provided here, the test vectors. This is important because if you haven't, even if you implemented the present yourself or you have taken the source code from someplace else, you have to check if it works correctly. So in order to do this, you have to check the test vectors, which is really easy. But of course these test vectors are for the full cipher, but in our experiment you need to shorten the cipher to 4 rounds because we will be trying to experimentally verify a distinguisher that is valid for 4 rounds of present. So we have already discussed these parts. What we were trying to prove is the validity of this 4-round iterative characteristic for present. So what you need to do is actually, I think I already, summarized it here. So what you need to do is take a plain text, which you should probably generate randomly. Actually here we already discussed this in the lecture. Here you can see that the experiment starts within a for loop for randomly generated 100 keys. You randomly generate n plain text pairs and do this experiment in this way. But of course you can always switch these two for loops. Instead of starting the loop for keys, you can start the loop for randomly generated plain text and use that plain text for 100 keys. It is your choice, but you need to realize that you don't need to store generated plain text, because all we need is to do, take the plain text, encrypt it, and check the results. So you don't need to store any plain text and ciphertext. So the code you are going to write actually shouldn't be using much memory, because you don't need memory at all. All you need is to store 100 counters, which is very simple. Okay, so idea is this. We have this distinguisher which says that if you have a plain text and if you flip 2 bits of that plain text, so this way obtain a second plain text. If you encrypt both of these plain texts with the same key, after 4 rounds, if you XOR the outputs of these 2 plain texts, then you will see that their output difference, their XOR, have only 2 ones in their XOR, so belonging to these 2 places. But this happens with probability, a theoretical probability, which is 2 to the minus 80. So this homework is just to check if this theoretical obtained result is correct in practice. So depending on the experiment output, you can decide this. So if you perform this experiment and observe that this probability in practice is actually something like maybe 2 to the minus 25, then this would mean that the theoretical result does not apply in practice. And this way you can say that, okay, the papers that are using this distinguisher actually not that correct. The complexity should be a lot higher. But if you obtain something like even better, like 2 to the minus 10 perhaps, then you can say that, okay, the theoretical result actually works a lot better in practice, so the attack provided in these papers can be improved in this way. But mainly what we are trying to see if this probability is somewhat correct. So our aim is to obtain in practice if the practical probability matches this one. Okay. So you can first repeat this experiment for a single key and see that it works. Then you can repeat the same experiment for 100 keys just to be, just to be sure. So idea is as simple. Let's talk about for a single key first. You randomly generate n plaintext pairs. You can find many random number generators. Even you can use the built-in random number generator for the programming language that you are using, but just print some of the randomly generated plaintext on the screen to see if the random number generator works correctly. For instance, you are trying to produce 64 bits here, but maybe your random number generator actually produces 32 bits. So this might actually give some wrong results for this experiment. So all you need is a for-run encryption of present. So you generate your plaintext PI, then flip its 2 bits to obtain, let's say, PI prime. So you take these 2 plaintexts and encrypt them. So you have encrypt PI, you encrypt PI XOR alpha. The result is, let's say, ciphertext I and ciphertext I prime. You XOR them and check if it is beta. But in this experiment, alpha equals to beta. So all you are checking is if the output difference has only 2 ones at the places here. Okay. If this is the case, just increase your counter, which is initialized to 0, so it becomes 1. So we repeat this experiment many times. So since the performance of the code depends on your implementation, if you choose a really large, it may take a very long time. But you know that since the probability is 2 to the minus 18, n should be larger than 2 to the 18. So my suggestion is to run this experiment for something small first, like 2 to the 20, and record how many seconds it takes to perform 2 to the 20 operations. And also check if your code is running correctly. So once you have this, observe that the code is running correctly and measure the time, now then you can increase n and wait maybe hours to get the result. Because if you don't do this, if there's a simple programming error, you can wait many hours and at the end obtain a very bad result. So this is why I'm suggesting you to, make a toy example first and then run for the real code. Once you do this, you will obtain this counter. If it is something looks correct, then you can repeat this experiment for 100 keys and then take the average of the CIs. So what does this mean? You know that the expected value is actually the probability this times n. This is your expected value. When you perform an experiment in real life, the value you observe here, the average of CIs, is actually should be the expected value, should be something close to expected value. So once you perform the experiment, you have the expected value E, which is actually in this scenario the experimental observed value. You also have n because you choose it. It depends on you. But you have 2 parameters, but your equation has 3 parameters, which is E equals to n times P. You know E, which is the average of CIs. You know n because you chose it. So from there you can obtain the practical probability and see if it matches this one. As I told you, if it is worse than this, like 2 to the minus 30, let's say, this means that something wrong with the theoretical obtained result. If it is like 2 to the minus 5, let's say, then you will say that, okay, this works a lot better in practice. Sometimes this happens. There are many reasons that this might be observed, because we obtain this theoretical result because we observe that there is a path going from here to here with this probability. But maybe there's another path. Instead of going this, it goes someplace else, but goes back to here after 4 rounds. So maybe this is in practice somewhat better. So this is the idea of the experiment. We are trying to see if this is the case. So if you obtain something really good, like 2 to the minus 10, this means that practical results are better than the theoretical ones for this single scenario. But if you obtain something this really close to this, it is also correct. I mean, some people ask me if they are doing something wrong, if they obtain something like this. No, you're not wrong. This means that theoretically obtained result matches the practical result. So this is a good thing actually. So this means that the paper that uses this distinguisher theoretically actually correct in practice. So this was the idea in the first place. We wanted to see if theory matches the practice, and in this case it matches. Remember that we obtained these probabilities with an assumption that these are independent events, but actually once you are given the input difference here, actually these runs are not independent from each other. And I told you that although this assumption is not correct, it works in practice. So in this experiment you will see that this theoretically obtaining probabilities for the characteristics is actually works in real life. So at the end, just obtain the practical probability and then submit your homework. I told you that we are expecting to obtain something close to this, but how close to it depends on the practical experiment, and your job is to see what it is. Okay, so I didn't have received any other questions about this homework, so these are actually the things that I'm going to answer in this video. In the future weeks I will talk about impossible differential cryptanalysis, but before that we will be having the second homework. We already discussed this at the class, but I haven't finalized it yet, so you can practice on it if you want, but I will verify it myself and see how long it takes for the code to run, and if it exceeds like a few days, then I will simplify this homework. But if it turns out to be something really fast, then I will submit it in this way. But recall that in this homework I'm going to give you the ciphertext pairs. Then you will try to capture the key yourself. So without the pairs that I'm going to give you, you cannot do the homework yet. But if you want to do it beforehand, you can generate the plain ciphertext yourself, and try to see if you can capture the key bits just to do the homework earlier. So I will try to do this in the following weeks. Okay, so then we will see if this wrong key randomization hypothesis is really correct in practice. Okay, so but when the homework 2 is finalized, I will post it in the auto class so you will see it. Okay, and one maybe last announcement about our lectures is that our final date will change, because I'm expecting that university won't open its doors before July. So I don't think that we cannot get together before July, and I don't want to do this exam online. And university now, they're considering many options, and most likely one will be to push the semester to the end of summer. So I'm expecting that we will have our final exam around some time in August or September. So actually the latest time that we are allowed, so that we can get together again and have the exam together in a classroom. Okay, until that time we will continue our lectures in this way, and I will keep giving you this kind of homeworks. But once you get used to the first homework, the following ones would be much easier to implement and obtain the results. So if you have any more questions, please use the discussion board in the auto class, and I will try to answer your questions there. And if you have any other questions related to the course or anything, just submit it there, and I will try to answer it by either answering there or in my following videos and give you the correct answers actually. So I think this will be all for our first lecture. So next week I'm hoping to record a video about impossible differential cryptanalysis. I will tell you how it works, and I will give a few examples, and maybe in the future our third homework will be about impossible differential cryptanalysis. Okay, I hope you are all well, and as I told you, please stay in home unless it's absolutely necessary. Hope to see you soon.